Great.
I'll just wait a few seconds for people to pop in. All right. As I said, we'll wait just a few seconds for everybody to get their audio and video clicked on so we're ready to go. All right, welcome everybody to the Prosthetics and Orthotics session here at Virtual ASB. My name is Dustin Crouch at the University of Tennessee. I'll be the moderator, and I'm joined by Helen Huang at the University of Central Florida and Daniel Jacobs at Temple University as co-moderators. So welcome everybody. I don't know all the total ground rules, but I think the main ones are if you have questions during the talks, which there'll be 3 blocks of talks. In each block, there'll be 4 talks. And then we'll go into a 10-minute or so question and answer. If you have questions during the session, you want to input into the chat window, please do that. You can also wait till the question and answer part and ask your question verbally by raising your hand, and then we can unmute you. And without further ado, we'll have our first speaker, Ying Fang, give us a talk on the effects of ankle exoskeleton assistance on metabolic efficiency of incline walking and stair ascent in cerebral palsy. You may go ahead when you're ready.
Okay, I need to mute myself so you can hear me now. Can you see the slides too?
Yes.
Okay, great.
Well,
no?
Not now.
Okay.
Was before.
Okay, 1 second. All right. Oops. So share screen. Okay, how about now?
Yes.
All right. Good morning. In this presentation, I will talk about how ankle exoskeleton affects walking efficiency on graded terrains in people with cerebral palsy. CP is the most common childhood physical disability and is characterized by movement disorders. Ankle dysfunction is very common in CP. Specifically, plantar flexor weakness is associated with poor walking efficiency that affect lifelong mobility and quality of life. Inclines and stairs are very common in our community. We use them to get to work, go shopping, or go on hike. Compared to level walking, incline walking and stair climbing require more energy and muscle work, which poses great challenges for people with movement disorders, including those with CP. Studies have shown that providing ankle assistance can reduce the metabolic cost of incline walking in unimpaired individuals. However, no study have investigated the effect of ankle assistance during graded walking in CP. Our lab developed an untethered ankle exoskeleton that can reduce metabolic cost of level walking in CP by 19%. In this study, we would like to see whether the device can make incline walking and stair ascent easier for this population. The lightweight untethered ankle device, as shown in the picture, weighs about 2.2 kilograms and can provide ankle torque up to 20 Newton meter. We put 4 sensors in the shoes to distinguish the stance and swing phase of a gait cycle. The sensors are also used to estimate user ankle moment. which has been validated across various terrains, including inclines and stairs. During stance, plantar flexor assistance that matches the user's ankle moment profile is provided. During swing, a fixed level of dorsiflexor assistance is provided. We had 7 participants with CP doing 2 exercises. One is 6-minute walk on 5-degree incline treadmill, and the other is 5-minute stair stepping on Stairmaster. For each activity, they completed 2 conditions at a randomized order: walking without a device and walking with a device that provides assistance. Before all conditions, they had 5-minute acclimation for each exercise with the device powered on. We calculated the net metabolic power and integrated EMG for the soleus, tibialis anterior, and vastus lateralis for the last 3 minutes of each condition. Here are some videos. Here are the metabolic results. The bar in the figure are the group average, and each line represents 1 person. All participants had reduced metabolic cost in both activities, with an average reduction of 14% for incline and 21% for stairs. For muscle activity, the curve here shows the muscle activation averaged by 7 participants. The bar chart represents integrated EMG of the group and shows that all 3 muscles had less activation in exo compared to shot. For stair ascent, soleus and vastus lateralis had reduced activation when walking with exo, but not tibialis anterior. In addition to the primary results, we found that participants who had greater reduction in incline walking also showed more reduction in stair ascent. This brought up the question of who are more likely to benefit from the device. To our knowledge, we did not notice any effects of baseline metabolic level or GMFCS level on metabolic reduction. Therefore, having a larger sample size can help to answer this question in the future. Another discussion point is appropriate level of assistance. We did a pilot test on the effect of assistance level on metabolic cost during incline walking and found that medium versus high or low assistance resulted in the greatest metabolic reduction. Future research needs to test more participants and perform the same analysis for stair ascent. Finally, I'd like to thank the PI and lab members who all contributed a lot to this project. Thank you for listening.
Great. That was a great talk, and thank you for keeping it to the 5-minute limit.
Yeah, thanks.
Next, we have Koller, who's going to tell us about quantitatively prescribed passive dynamic ankle foot orthosis and how it reduces total metabolic cost of transport.
All right, can you hear me?
Yes.
Okay, perfect. So good morning. As mentioned, my name is Koller. I'm a PhD student at the University of Delaware under the advisement of Dr. Elisa Arch. So stroke is a leading cause of long-term disability. And individuals post-stroke often have insufficient control of the shanks forward rotation during mid to late stance due to plantar flexor weakness. Passive dynamic ankle foot orthoses, or PDFOs, have a unique spring-like characteristic that could potentially replicate plantar flexor function by adding to the resistance needed to help control the shanks forward rotation during stance phase dorsiflexion. Controlling shank forward rotation can store mechanical energy during stance phase dorsiflexion and return this energy during push-off. This storage and return of mechanical energy can improve step symmetry and gait velocity and thereby potentially reduce cost of transport. Thus, if AFO use can improve an individual's cost of transport, such improvements may lead to greater levels of physical activity, improved quality of life, and reduction in healthcare costs in individuals post-stroke. Previous studies have only focused on clinically prescribed AFOs or AFOs with the same stiffness values for all participants. Why is not working? There we go. We have developed a prescription model that can quantitatively prescribe PDFO bending stiffness based off an individual's level of plantar flexor weakness. This study aims to quantitatively prescribe a PDFO while allowing them to wear the PDFO for 4 weeks and examine the effect the PDFO has on cost of transport and gait velocity, along with underlying joint level mechanisms compared to wearing their standard of care AFO and without wearing an orthosis. We hypothesize that gait velocity and cost of transport will improve towards typical, ankle joint parameters will increase, and hip joint work will decrease while wearing his or her PDFO compared to their no AFO and standard AFO conditions. So 5 individuals post-stroke participate in this study. The participants first came in for an evaluation visit where a gait analysis was completed to gather the appropriate data to manufacture the PDFO, collect data with wearing their current brace, and collect data without wearing any orthosis. The PDFOs are manufactured in carbon fiber, and the bending stiffness was prescribed by subtracting the participant's peak plantar flexion moment from the mean speed matched height normalized typical peak plantar flexion moment from our normative database, and then dividing this quantity by the average change in ankle angle during stance phase dorsiflexion or 12 degrees. The participants then wore this brace in the free living environment for 4 weeks, and the walking velocity used instrument treadmill is at the self-selected walking velocity determined without wearing an orthosis during a 10-meter walk test. So at the no AFO condition, or at the no AFO velocity, all 5 individuals improved their total cost of transport, seen as a decrease in cost of transport. And all 5 individuals improved their gait velocity, seen as an increase in gait velocity, while wearing their PDFO compared to their standard of care and without wearing any orthosis. A few participants did show the appropriate trends in certain joint level parameters while wearing his or her PDFO compared to wearing his or her standard of care and not wearing a brace. So for example, the participant 2 improved his peak plantar flexion moment. However, we did not see any changes in ankle joint work, but we did see for participants 2, 3, and 5 improvements in hip joint work. But in general, the participants did not show clear trends and had substantial variability. So this study showed that quantitatively prescribing PDFO bending stiffness based off an individual's level of plantar flexor weakness can improve mechanical cost of transport and gait velocity. However, we did see inconsistent results in the underlying joint level mechanisms, which may be due to the heterogeneity of this post-stroke population. So future work should collect more data as well as look at other parameters and on the contralateral limb. Thank you.
Excellent. Thank you very much. All right. Moving right along. We've got Ben Shuman next, and he's going to talk about a comparison of methods for evaluating ankle-foot orthosis stiffness.
Thank you very much. Can everyone hear me?
Yes.
Wonderful. Well, before I begin, we don't have any disclosures to make. So as the last presentation just gave a really good example of, we know that AFOs are prescribed to support ankle motion and augment functional deficits, and that as physical objects, their behavior is defined by the geometry and materials. And as was just clearly outlined, we really might want to know what those properties are so that we can really target good outcomes for various participants, in this case with plantar flexor weakness. But this begs the question, how do we know how stiff an AFO actually is? Well, it'd be really nice if this was published by the manufacturers, but it doesn't tend to be. And so we have to turn to the academic literature. But unfortunately, it's not exhaustive. And so many AFOs that we may be interested in, especially off-the-shelf AFOs, are not represented. And even if we do find the AFO we're interested in, we have another issue, and that is that testing isn't standardized in this space. And so here I'm showing you 3 different testing methods from the literature. And I think we can all readily appreciate that there's some serious differences in how this is being calculated, both in the motion that's being prescribed, what kind of constraints on that motion, and loading. So that begs the question of my talk, which is how does the stiffness of off-the-shelf AFOs differ across testing methods? And so we examined 3 different testing methods. The first one is similar to one of the ones I showed in the previous slide, where we hung weights. Now we're interested in individuals with reduced plantar flexion strength. So we deflected our AFOs into dorsiflexion. Here you can see our first method where we strapped our AFO to a plaster shank and we incrementally hung weights off of the toe and measured the deflection to calculate a rotational stiffness. We compared that to results that we got from looking at 2 different recent test fixtures in the literature, the SMAP, which comes out of the University of Michigan, and the Empire, which comes out of VA Puget Sound. And both of these clamp an AFO to a base so we can constrain motion to the strut. And then we rotate about a defined point or ankle axis using a linear actuator to apply a reasonably constant deflection velocity. Now, for all 3 of these methods, we tested the exact same 13 AFOs across 4 different manufacturers. And these were all off-the-shelf carbon composite AFOs sized large for a right foot. Well, what do we find? Well, for this plot here, what I'm about to show you has AFO stiffness plotted along the x-axis, measured in Newton meters per degree. So what is the moment it takes to rotate an AFO through a degree of motion? And then we have the AFOs we examine on our y-axis. So if we start by just examining our 2 test fixtures, the SMAP and the Empire, we can see reasonably good alignment in our stiffnesses. They certainly follow the same trend. And on average, they're about 0.31 Newton meters per degree different, which corresponds to about 14%. Now, there's obviously some outliers in here. We can see that with the Spry Step Plus, which was different by about 32%. Well, what happens when we throw in the hanging weights method? Well, the picture gets a little bit less rosy. And we can see that on average, most of our AFOs are measured as being significantly less stiff, but not always. And if we try to put some numbers to this, we can see that the differences in stiffness between the hanging weights in either the SMAP or the Empire test fixture, on average, are more than twice as big as the differences that we saw between the Empire and the SMAP each other. Well, what do we take away from this? Well, I think the most obvious thing is that not all test methodologies are really equivalent, and that this really prompts us to use some caution when we try to make comparisons across methods in the literature. We lack these testing standards, and so these different things may imply different alignments, different testing speeds, and different constraints on motion, and all of these can have an impact on your measured stiffness. For instance, I think that's particularly important with our hanging weights, where there was no defined ankle axis through which this is rotating. In the future, we're hoping to investigate some of these impacts, and I hope to present that in the future. Thank you. I look forward to your questions later.
Awesome. All right, we got one more talk in this block, and that is from Sanford, and he's going to tell us about vibrotactile feedback for improved control of myoelectric devices. Take it away.
Okay, do you guys all see my screen?
Yes.
Excellent. Hello, everybody, and thank you for coming to the presentation today. So yes, the title is Vibrotactile Feedback for Improved Control of Myoelectric Devices. This presentation will probably be a little bit different than some of the other ones because whenever I get asked what I study, I always have to state that, so I do not design prosthetics. We look to train people to use prosthetics better. And we do that through a variety of different ways, either through vibration cues or virtual reality to be a big one. So I'm actually going to present a slightly different protocol than what was submitted in the abstract. The research has kind of changed, but I do want to talk about what I submitted because I think it's a very important concept, and I think it's actually something that our lab will revisit in the future. It's the idea that when you apply vibration in real time, you can actually alter a user's proprioception or neurophysiological signals, such as producing an illusory movement or altering EMG. So through either indirect or direct vibration, you can have an effect on those muscle fibers. So our plan was to try to use that real-time direct vibration to improve myoelectric control. And if anybody read the abstract, it was basically the idea that we wanted to increase the classification accuracy in real time by increasing the separability of those classes that the user used to command the device. So right now, the primary research that we do, or that I do, is we look to develop these novel multi-sensory feedback approaches. We do that by leveraging select features of visual and vibrotactile feedback within these immersive environments. And the two main features that we're looking at are between simple and complex, and continuous and bandwidth. And I have underlined continuous and bandwidth because I'll circle back to that one here in the next couple of slides. So the methods behind, hopefully this slide's not too wordy for you guys, but the main idea is that the participants are commanding a virtual myoelectric prosthetic through various reaching tasks, and they do that through the mapping of the isometric muscle activity to direction intent. So the subject here is wearing a restrictive upper body brace. 14 EMG sensors are on the upper body, wearing a VR headset as well as an EEG cap, and controlling this device in the VR body, or excuse me, in the VR environment. And then the addition of vibration motors support the visual feedback for trying to guide the participant to the shortest path between targets. So I have a couple of videos here, and I'll play them both at the same time here in a second, but real quick. So we talked about comparing different visual feedbacks, or leveraging the leveraging select features of visual feedback. So I'm looking at a couple of different comparisons, and I can't go into too much detail because I certainly don't have enough time, but it's the idea of complex continuous or complex bandwidth visual feedback to see what is ultimately going to help train the person to have better myoelectric control. And all participants complete a pre-test, training, and a post-test phase. So if you see here in both the videos in this top one, this is what we call continuous feedback. There's a transparent arm or a ghost arm that is always visible, and it is always on the shortest path length. And the subject can see it, is very aware of it, and will go to it to make corrections. Here in the bottom video, what we call bandwidth, the participant actually is only provided visual feedback once their air is really high. If they're right on top of the target, they don't see anything. It's only once they really start to screw up. And this goes into one of the general theories of motor learning called the guidance hypothesis, and it takes other theories into account, but it's the idea that we want to reduce the reliance on the visual feedback for the subject to develop those intrinsic mechanisms such as muscle memory or proprioception to have better control. So moving on, the current study, we're still in the preliminary stages, so unfortunately I do not want to discuss those results, but it is based upon a previous study for a movement task that has been published, where we found that bandwidth feedback does show potential to improve short-term retention relative to a training baseline. So ultimately, just to wrap things up, what we are interested in, once again, is kind of leveraging those select features of both visual and vibration feedback to accelerate motor learning. What you guys saw today was really only visual feedback, but the future studies look to add that vibrotactile feedback back in kind of a novel way to not only, or we will look at that not only independently, but in conjunction with visual feedback to create those novel multisensory feedback platforms. So we are taking a little bit of a different direction than what I spoke about originally, but we still hope to include everything to, once again, looking to accelerate that motor learning to improve the myoelectric control. All right, thank you guys. Oh, and yeah, thank you. And if anybody wants to contact me, that is my email.
Great. That's awesome. We started late, so I want to give time for questions. Let's maybe jump to ones in the chat, and a reminder, you can raise your hand if you want to ask a question verbally.
All right, thank you. Yeah, please keep them flowing in. Our first question is for Ying from Rebecca, saying that 11 to 33 years seems like a large range. Are there known differences in walking between children and adults with CP? If so, perhaps age is a factor that would help answer the question, who benefits most? Do you plan to narrow your inclusion criteria in the next study?
Thank you for the question. So after I saw it, I actually went back to the demographic table. So from the study, I don't really record any significant differences between our child participants and adult participants. So in our cohort, we have 5 kids under 18 and another 2 are above 18. And what really stands out is actually the GM-FCS level. So for participants who are at GM-FCS level 3, their walking speeds are significantly slower than the other 1 and 2. So that's for, yeah, that's the difference. And age could be a factor. Actually, I was also looking at that plot, so the plot that's showing the relationship between two reductions in stair ascent and incline walking. And I don't think based on our cohort, there's a relationship of age. I guess age is not an effect that affects who's benefit most. So for future study, I think especially when we started doing large clinical trials, I think the age will be definitely a factor to look at, and we will be more strict with our inclusion criteria. So far, what we've been doing in the lab are mostly feasibility studies, and I can see the benefit of include everyone, so we can see who can benefit from the study, and especially the participants. They're just enthusiastic about participating in and want to try it out. So I think at this stage, include them is not a bad idea. But future, yeah, when we're collaborating with hospitals, then we should be more strict about inclusion criteria.
Okay, thank you. Our next group of comments go to Corey. I'm going to combine ones from Kristen and Elena, looking for more information about the PDAFO bending stiffness. Was it linear? How well did it compare to the prescribed AFO stiffness? And then following with the other talks in the block, is there a way to determine optimal stiffness?
Yeah, so in regards to how did the bending stiffnesses compare? So as I mentioned, I had 5 individuals. 2 of them were currently prescribed a hinged AFO, which means there really wasn't a defined stiffness to them. A third one was a solid AFO, which means very stiff. However, 2 of them were kind of a similar design, and ours were slightly more compliant. And ours was a linear bending stiffness. In regards to determining optimal, if I'm understanding your question right, I'm just going to quickly share my screen, in that this is how we were defining bending stiffness, and that we were taking, their current peak moment that they walk without wearing a brace minus from a typical speed matched height normalized, and then over a typical angle. Now, I guess to expand on that a little bit, we do understand that in post-stroke walking that they achieve better, more efficient gait when they walk faster. So this is kind of one part of my dissertation, but we are looking towards, if we increase velocity, do we see more improvements, and trying to explain those information. And that's kind of a work in progress. But I think that will get into how do we determine optimal stiffness when we kind of look at a range of conditions.
Great, thank you. And our next couple of questions, I'm trying to get at least one into everyone before we run out of time, so sorry for moving a little fast. But the next set of questions are for Ben. So Thomas and Josh asked similar questions too, looking at, can you say more about the variability between testing methods? Are any, superior with regards to variability, repeatability, ease of setup? Josh specifically is wondering why perhaps the hanging weights were so inconsistent compared to the other 2 methods.
Sure. Well, when we start talking about is there a gold standard testing method? And I think that's kind of the problem. There isn't, right? And each one has its advantages and disadvantages. I know for the SMAP and the Empire. So I built the Empire, and Dee Matoda built the SMAP. And hers is a more complicated device, to be perfectly honest. But I think for ease of setup, we're actually pretty comparable. I actually found the hanging weights method to be more difficult than our test fixtures, but it certainly has less investment in developing the setup. Getting towards the question of why the hanging weights was so inconsistent, it was a much less constrained system. So especially for these AFOs that are not hinged AFOs that don't have a defined ankle joint, you're just deflecting the strut. And so we actually get a lot of out of plane motion in there. And we did our best to compensate for that in our calculations, but you're not rotating about a single point in the same way you were with either of these two test fixtures. With this in there, there's a question about repeatability and variability. I know both Dima and I did quantify test, retest reliability in the journal articles that are out about these. And we have pretty comparable repeatability. So what we're actually seeing here, I'm pretty sure, is just differences in methodology and what we're actually getting out of our test setups. We're able to get highly reliable results between testers and tests for both of these devices.
All right, I think I'm gonna cut it off there. As a reminder, we also have a spatial chat after this to talk about all the questions we didn't get to, so please go there. Otherwise, we're gonna move on and turn it over to Dr. Huang to introduce the next block of speakers.
Great, thank you. So the next speaker is Ross Miller. His talk is Transtibial limb loss retains a normal metabolic cost in 3D simulations of walking.
Muted.
You're muted, by the way.
Okay, I'm obligated to disclose this was a DoD-funded study, yet the views expressed here are not those of the DoD or anyone other than me and Elizabeth. So I think there's about 80 people in the chat here. If I were to ask each of you what happens to the metabolic cost of walking after limb loss, I would guess most of you would say it increases or goes up. And I say increases there a little facetiously because there's no longitudinal data on this, right? These are all comparisons of cross-sectional metabolic cost, folks with limb loss and folks without limb loss, and then the assumption that energetically the folks with limb loss used to be like the ones without limb loss energetically. And that's generally, if you're okay with that assumption, that's generally borne out in what you see in the literature on the metabolic cost of walking with unilateral transtibial limb loss. Here's 8 studies shown here, and the blue bars are the ratios of metabolic cost for the limb loss group versus the non-limb loss group. And you can see that there's anywhere from about a 5 to up to about a 40% greater metabolic cost in folks with unilateral transtibial limb loss. Now, the interesting part here to me is that most of these populations that were studied here with limb loss also had some other comorbidities or confounders that independently affect metabolic cost aside from limb loss itself. Now, what if we could get rid of those? What if we could study folks that don't have those confounders? Would they still have a high metabolic cost of walking? Well, maybe, maybe not. Study 9 here was in children with limb loss who lack a lot of those health-related comorbidities, and they didn't find a very high metabolic cost of walking, although I don't emphasize this one here because study 8 was also in children. They found pretty high cost. But studies 10 and 11 here were in relatively young, relatively otherwise healthy and fit military service members, and they had statistically at least the same metabolic cost as the able-bodied group, as the non-limb loss group. Study number 10 here was one by my co-author here, Elizabeth Russell Esposito. Now, this was really interesting to me. I discovered these studies some years ago here, and it got me thinking, what if we could isolate the effect of limb loss? What if we could study the limb loss in isolation? So study individuals where they have nothing different about their body other than that they've lost a limb, nothing else changes, which of course is kind of a contrived situation. You can't really go through limb loss and the recovery and all that and then still have nothing changed about your body. But hypothetically or scientifically, it'd be interesting to be able to isolate that. Now, we can only really study that using computer models. And so that is what we did here. We developed a three-dimensional open sim model based on Apurva Rajagopal's model and modified it to have a unilateral transtibial prosthesis like you see in the model on the right here. Essentially, the right ankle muscles were removed and the right ankle torque angle relationship was replaced with one approximating a generic transtibial prosthesis. Should you believe this model, we validated it by examining the pre-limb loss model, so the one without limb loss, and seeing if we could have it predict small changes in metabolic cost compared to things in the literature, such as adding mass to the feet, and it did pretty well there, or such as bracing the ankle. Now, these things aren't exactly the same as walking with the prosthesis, but they are things that we could compare to in the literature that are relevant to prostheses. You know, prostheses have different masses than a biological leg. Prostheses have different stiffnesses at the ankle than a biological leg. So we then performed optimal control simulations of walking with and without limb loss using the new OpenSim MoCo software. In a 5-minute talk, that's about all the methods that you're getting. But one thing that we did here that I want to emphasize is that not just everything other than loss of the limb was identical between these models, but the method of generating the simulations and the cost function was identical between the models. They were tracking or attempting to track the same able-bodied gait data, and they had the same relative weighting or relative emphasis on tracking the data versus minimizing the muscular effort used to track those data, which may not necessarily be replicating how folks with limb loss walk, but it's what we were attempting to do here, again, to keep everything the same or as the same as possible as we could between the models with and without limb loss. Now, because it's got a prosthesis here, you can look at this and easily say which is the one with limb loss, but I would wager if I took the prosthesis away here and didn't show it to you and put some fake muscles down there, it might be like a little difficult to tell which one is the one with limb loss. And so the model with limb loss was able to track the non-limb loss experimental gait data pretty well. Now, what happened here with metabolic cost? We did this with 36 quote unquote participants, which is really just different parameter sets of the model, different muscle model parameters and things like that. The solid lines are participants or virtual subjects whose metabolic cost increased on average with limb loss, and the dashed lines are participants who decreased after limb loss in their simulations. And outside of a handful of exceptions here, you can see there really wasn't any large changes in metabolic cost with limb loss here. So pre-limb loss or post-limb loss, on average in the red here, had statistically the same metabolic cost. So no consistent or no large average statistical difference here in metabolic cost pre-limb loss versus post-limb loss. So main finding, unilateral transtibial limb loss did not increase metabolic cost of walking in a 3D open sim model set up in an attempt to isolate the effect of limb loss itself. Implications of this, high metabolic cost of walking with limb loss may not be due to limb loss per se. I think it's more likely to be due to secondary changes that often accompany limb loss, such as strength and fitness or prosthesis issues. I think that's important because while we can't predict limb loss or really prevent limb loss in a lot of cases, we can affect and possibly prevent some of these things. We can have an effect on strength loss after limb loss. We can have an effect on fitness after limb loss. We can have an effect on the quality of the prosthesis and the fitting of the prosthesis after limb loss. What's next? We'd like to isolate how exactly the model accomplishes this. We've done a fairly superficial dive into that I don't have time to get into today, but we haven't really isolated the mechanism behind how the model is able to accomplish this in most cases. I'd like to include some additional goals such as balance and stability. And importantly, I'd like to follow this up examining transfemoral limb loss. Now you might think transfemoral limb loss, this has no chance of having the same metabolic cost as non-limb loss. But if you look into studies that compared very fit, relatively young, high functioning folks with transtibial limb losses versus controls, yeah, on average, they're higher, but it's not dramatically higher. So I think it is possible within this framework that we could indeed see very similar metabolic costs, even with the more dramatic transfemoral limb loss case. I'd like to thank my collaborators, Elizabeth and Wyatt, and the OpenSim MoCo team, Chris and Nick. This is, if you want to get into doing these types of simulations, go to DuckDuckGo and search for OpenSim MoCo and learn how to use it. It's really, really amazing software they put together to do these types of simulations. Thank you.
All right. Packed a lot into that talk. Let's move along to the next speaker. We have Anthony Anderson. His talk is pilot tests of robotic prosthetic ankle with parallel elasticity and offboard actuation.
Can everyone hear me and see my screen?
Yes.
Okay. Thanks for the introduction, Dr. Huang. Like she said, I'm Anthony Anderson from the University of Washington and the VA Center for Limb Loss and Mobility. And today I'm going to talk about some of the work that our group is doing to develop a prosthesis that mimics the function of the gastrocnemius muscle at the knee and ankle for transtibial amputees. So the gastrocnemius and the soleus are the primary plantar flexor muscles of the human calf. And while the soleus crosses the ankle joint only, the gastrocnemius crosses both the knee and the ankle. And there's a lot of great research out there into the synergistic functions of these muscles during gait. However, modern prostheses for transtibial amputees do not have any elements that replicate the action of the gastroc at the knee. And it's unknown how the loss of this muscle affects amputee gait. So our group previously built a prototype of a biarticular prosthesis that mimicked the gastrocnemius's effect on the knee and the ankle with a clutched spring system that crossed both joints. And during our study, we found that many of the parameters that affected the overall device behavior were hard to experimentally control. So for example, changing the stiffness of our biarticular spring was a really clumsy process. And the ratio of the knee and the ankle lever arms were fixed. They were built into the device. And that's important for biarticular muscles. So to address the issues with our prototype, we're moving to an offboard actuation system approach. And we've built this system shown here with these powerful offboard motors and controllers that can actuate lightweight wearable devices as a person walks on a treadmill in our lab. And this system uses two flexible Bowden cable actuators to provide these device torques. So we're pairing a knee flexion exoskeleton with a powered ankle and then coupling them in our control software to behave like virtual muscles. With the offboard robotic system, we can render a virtual soleus and virtual gastrocnemius and easily change their stiffnesses, activations, and attachment geometries in software. And we intend to use this system to explore basic science questions about the biomechanics of biarticular muscles in amputee gait. Much of the system is still under engineering development, so with my last few minutes, I'll just tell you a little bit about our active ankle design. Our custom ankle joint attaches to standard clinical prosthesis hardware, including the foot plate and the pylon connectors you can see here. Our device weighs around 1 kilogram, depending on what side of foot plate is attached, and it has a peak plantar flexion moment of around 175 Newton meters. The joint is a parallel elastic actuator, meaning that it uses some custom dorsiflexion springs in parallel with the Bowden cable. And we went with this design approach so that we could independently modulate both the plantar and dorsiflexion moments in our control software. And this video is showing one portion of many benchtop tests that we've conducted to characterize the mechanical behavior and the controller performance for this device. This video shows a healthy subject walking on our device using some prosthesis simulator boots. And in this test, the device was emulating a virtual torsion spring at the ankle joint. So it behaved kind of like a passive prosthesis. And these types of tests are important from a systems engineering perspective, just to ensure that the device can handle the demands of walking in terms of hardware and software. As we conduct these experiments, we see a lot of things that confirm that our device is working the way we want it to. So these two plots show ankle angle and ankle moment across the gait cycle, as measured with the onboard sensors from the device over 3 different stiffness conditions. In each condition, we see normal ranges of motion and peak torques for this walking speed, as well as several other standard features of the intact ankle during walking. So for example, we see the ankle move slightly into plantar flexion following heel strike, and that's paired with a small dorsiflexion moment before rolling into a dorsiflexion angle and providing a large plantar flexion moment at push off. So speaking generally, I think that we're ready to start using this device in experiments with subjects with lower limb loss. Right now, we're working on repeating a lot of this evaluation work with our knee flexion exoskeleton. From there, we'll be integrating the 2 devices into our next-gen biarticular prosthesis and moving forward to human subjects experiments at the Seattle VA hospital. And again, our long-term goal is to use this device to explore how a virtual gastrocnemius might improve amputee gait. If you'd like to contact me with any questions about what I presented here, you can reach me via email or Twitter, and I'll stop there. So thanks for listening to my talk.
All right, great. We're just going to keep moving along here. Next speaker is Kara Ashcraft. Her talk is effects of prosthetic stiffness and added mass on metabolic cost and symmetry in female runners with a leg amputation.
All right, thank you. Good morning. Quick disclaimer. So in order to run, people with a transtibial amputation require the use of running specific prostheses, or RSPs, which are carbon fiber in series springs that attach to the residual limb. And the compliance or the stiffness of that RSP determines the amount of energy that's stored and returned during running, and are prescribed to patients by stiffness categories dependent on the user's body mass and their intended activity. And conserving mechanical energy via elastic mechanisms theoretically reduces the metabolic cost of running in athletes with two biological limbs. However, regardless of the RSP's ability to store and return energy, prior work by Beck et al., shown here with RSP stiffness on the x-axis and net cost of transport on the y, has shown that RSP stiffness has no effect on the metabolic cost of running in athletes with a transtibial amputation. Yet, Beck et al. Also found that the metabolic cost of running was reduced when the average peak and stance average vertical ground reaction forces were decreased, where decreased RSP stiffness resulted in lower stance average vertical ground reaction forces when compared to the recommended category stiffness. Additionally, Beck et al. Found that a decrease in peak vertical ground reaction force asymmetry correlated to a decrease in net metabolic power in runners with a transtibial amputation. Alcantara et al. Investigated the effects of adding mass 10 centimeters from the distal end of the RSP, which they found had no effect on peak vertical ground reaction force symmetry, but increased metabolic power during running at 2.5 meters per second. However, only 23% of subjects involved in studies looking at the effects of RSP in running are female, and none of the current studies account for these gender differences in their results. So to better understand how RSP configuration specifically affects women with a transtibial amputation, we measured metabolic power and kinetics while female runners use RSPs with different stiffness categories and with and without mass added to the RSP. And based on prior studies, we hypothesized that the use of a less stiff RSP without added mass would result in the lowest net metabolic power, but would have no effect on peak vertical ground reaction force symmetry when compared to a more stiff RSP with added mass. So to test these hypotheses, 3 female athletes with a transtibial amputation participated. Subjects ran on a force measuring treadmill using their recommended category stiffness, 1 category less stiff and 2 categories less stiff. We calculated average steady state metabolic power and then added 100 grams, 200 grams, and 300 grams, 10 centimeters from the distal end of the RSP category that resulted in the lowest metabolic power, and repeated the running protocol. We then calculated peak vertical ground reaction force symmetry index between the affected and the unaffected leg for all conditions, using the standard equation where 0 represented perfect symmetry. So my results will show each subject in colored dots with group averages in black dots. And in all graphs, the RSP conditions are going to be on the x-axis. So we found that on average, net metabolic power here on the y-axis decreased by 4.1% when using 1 category less stiff and 5.1% when using 2 categories less stiff when compared to their recommended category. When subjects used their most metabolically efficient stiffness category, net metabolic power decreased 6% when 100 grams were added, 4.5 and 4.7% when adding 200 and 300 grams, compared to, again, that recommended category, making this less stiff RSP plus the 100 grams the most metabolically efficient. So here with peak vertical ground reaction force symmetry index on the y-axis, we found that it decreased from 11.3% when using the recommended category to 10.3 when using 1 category less stiff and 6.6% when using 2 categories less stiff than recommended. When we added mass to the stiffness category with the lowest metabolic power for each athlete, average peak vertical ground reaction force symmetry index decreased from 11.5% with 100 grams added to 10.3 and 10.0%. Sorry, where am I here? Sorry. sorry. Whatever, the most symmetric peak vertical ground reaction force occurred when the athletes used two categories, less stiff than recommended with no additional added mass. Sorry for that. So from this preliminary data, we reject our first hypothesis as we found that a less stiff RSP with 100 grams of added mass resulted in the lowest metabolic power for our female athletes. And we also reject our second hypothesis as we found that peak vertical ground reaction force became more symmetric when athletes used an RSP that was two categories less stiff than recommended without added mass. So these findings then suggest a possible trade-off, right, between optimizing the metabolic power and reducing that leg asymmetry during running due to the different RSP stiffnesses and the mass in female athletes with the transtibial amputation. So with that, I'd like to thank my funding sources and thanks for listening. Sorry for getting lost.
All right, no worries, great recovery. I also want to say, I think I mispronounced your name. It's not, I think I said Kara, it's Kara, right?
It is Koller, yes.
Okay, so Kara Ashcraft, thank you very much. All right, we're gonna move to our last speaker of this section. It's Paulo Taboga. Hopefully I got that one right. His talk is prosthetic legs are shorter than biological legs during running and sprinting.
Okay, thank you for the introduction. Can you all see my slides? Okay, so good morning, everyone. And let me start by thanking my colleagues whose work was fundamental for this project. So traditionally, leg length is measured as the vertical distance between the greater trochanter and the floor. And this initial leg length is then used in models such as the spring mass model to understand the biomechanics of running. So in this model also, it is typically assumed that the leg length at touchdown is the same as the leg length at takeoff. So here we propose a model that represents better the anatomy of runners and sprinters first by measuring the leg length when standing from the hip joint center to the bottom of the foot. In addition to that, as you can see here, biological ankles can actively lengthen the leg during running by active plantar flexion. We therefore suggest to actually measure leg length at touchdown, mid-stance, and takeoff as the distance between the hip joint center and the point of contact of the foot with the ground. As opposed to biological ankles, running-specific prostheses cannot actively plantar flex. So we wanted to know if this functional difference is actually limiting the running leg length in athletes with amputation. And athletes with unilateral amputation offer a perfect way to test this, comparing the biological and prosthetic leg lengths within the same individual. So we measured the standing and the running leg length at touchdown, mid-stance, and takeoff of both legs for 10 athletes with unilateral amputation. So we found that athletes with unilateral amputation choose a standing prosthetic leg length that is 3% longer than their biological leg length. So here you can see the running leg length in meters at different speeds. And I indicate here the number of subjects who completed our trials at each speed. The regression lines are derived from linear mixed models that include all subjects. And I also include here the average leg lengths measured for all subjects during standing for comparison. So at touchdown, prosthetic and biological legs had no statistically significant difference across speeds, but they were 4% and 7% longer than their respective standing leg length. In addition, we found that the biological leg lengths increased as speed increased, while the prosthetic leg lengths decreased as speed increased. At mid-stance, both biological and prosthetic leg lengths were between 4% and 7% shorter than their respective standing leg lengths, but the prosthetic leg lengths were 3% shorter than the biological leg lengths during running across all speeds. In addition, biological leg lengths increased the length as running speed increased, while prosthetic legs decreased their length as speed increased. Lastly, at takeoff, we found that prosthetic and biological leg lengths had no statistically significant difference across all speeds, and they were between 4 and 7% longer than their respective standing leg lengths. And we also found that prosthetic leg length increased as running speed increased. And we found no effect of speed on the biological legs. So we were then able to combine standing and running leg lengths and calculate what the standing prosthetic leg length would be compared to the biological leg if we match the running leg lengths at touchdown, mid stance, and toe off. And what we found was that in order to match running leg lengths, prosthetic legs need to be on average between 4 and 5% longer than the biological leg during standing. Athletes with amputation, in fact, self-select the length of their prosthetic leg to be 3% longer than their biological legs, indicating a good agreement with our model. So in conclusion, our results suggest that using a fixed measure for leg length collected during standing does not reflect what is happening during running. We found that both biological and prosthetic legs are between 4 and 7% longer at touchdown and takeoff compared to their standing length. In addition, in athletes with unilateral transtibial amputation, our model suggests that their prosthetic leg measured during standing needs to be between 4 and 5% longer compared to the biological leg in order to achieve the same leg length during running. And with this picture showing an example of leg lengths that are prosthetic legs that are longer compared to the biological legs during standing, I thank you for your attention.
All right, great. Thanks to all 4 speakers in this section for their great talks. Dustin's going to take over with the questions. For the last 2 speakers, don't forget, put your questions in. Even if we don't get to them, I'm sure they'd love to get some feedback.
Great, yeah. Ross, I hope you were tracking all the questions because you got a ton, but some of the, maybe 1 or 2 we can address. There was metabolic cost questions. Basically, what went into your calculation? What did you use? And did you normalize by the body weight with or without the prosthesis?
The metabolic cost is calculated using Brian Umberger's model. And the data that I showed here were scaled by biological body mass, which is in the pre-limb loss case, it's everything. In the post-limb loss case, it's excluding the mass of the prosthesis. That's done because most of the studies motivating what we did here also used that same definition of metabolic cost for the folks with limb loss. If you don't do that, if you scale by total mass, which includes the prosthesis, then you get a small but statistically insignificant decrease in metabolic cost with limb loss. And if you don't scale at all, if you just express metabolic cost as joules per meter, which I'm not really aware of anybody doing that in limb loss studies, but if you do, then you get a pretty large decrease in metabolic cost with limb loss because because you have a smaller mass of muscle, I think, consuming that or there to spend energy.
Great. For Anthony, does your emulator also consider the compliance of the Achilles tendon? Did you set a single gastroc stiffness value or is it time varying?
So right now, the structure of my controller has a single passive stiffness in parallel with a force profile that we can arbitrarily vary to look like whatever we want it to look like. So if we were accounting for the series elasticity at all, it would have to show up in the time varying force signal. But this is ongoing work. I'm still trying to figure out how to control this thing.
Okay, a couple of questions for Paolo. Did you try using a nonlinear models when investigating leg length across speeds?
Great question. Yeah, we were thinking about that, but these graphs here can be a bit misleading because different subjects were able to reach different speeds. So the faster subjects were males and they were taller. So here the points represent less subjects. That's what's probably a bit confusing. But yeah, we were thinking about probably including some non-linear models to account maybe for that. But yeah, that's a good point.
Awesome. Thank you for our speakers. Maybe I'll ask another one. Going back to Ross, what sort of, I like this question here. So even though you found group-wise that there was no difference, some increase and some decrease, what were the factors that were responsible for those individual differences?
Great question. Don't know. There were 3 of the 36 subjects here, and I'll touch on BJ's question here. The subjects here weren't really like representing people. They were just some random perturbations to some of the model parameters, just to give some confidence that the main effect here was due to limb loss, not to what we assumed initially about the model's parameters. And so I wouldn't really think of these as subjects per se. It's more so kind of a limited sensitivity analysis. So there were like, if you look at the graph I had there, I think were like 3 models that had fairly substantial increases in metabolic cost, and then maybe 1 that had a fairly substantial decrease in metabolic cost, and nobody else really did anything. I can't find anything about those 4 particular models that are outliers in any particular way. And their results also aren't particularly unusual in terms of tracking the data well or anything like that. They all tracked it fairly similarly to most of the other models. So still looking into why some of them have notably different results than others. So long story short, I don't know.
Thank you.
All right. So I think Dustin wants me to hand this off to Daniel for the next set of talks. I want to point out, Kara, you do have a question in the chat, even though we didn't get to it. Okay, Daniel.
Thank you, everyone. It's been a great set of talks. I'm going to introduce the last group quickly, remind people to please join our spatial chat afterwards. Our first speaker is going to be John Shuman. Can you hear us, John? You're in the chat. Well, in case he's having technical difficulties, why don't we move him to the bottom? That way we can keep ourselves on time. And if we can start with Janet Zhang, that would be great. And hopefully we can get this going and stay on time here.
Okay. Can you all see my screen?
Yes, and we can hear you. Thank you.
Okay, great. Hi, everybody. My name is Janet, and today I'm going to talk about visual feedback and people with unilateral transtibial amputation. For people with unilateral transtibial amputation, have lower peak propulsive force in their affected versus their unaffected leg during walking, which leads to asymmetric biomechanics and higher metabolic costs for them. Several studies try to use real-time visual feedback to modify the walking gait for people with lower limb amputation. In other populations, such as stroke patients or elderly people, using peak propulsive force as a real-time visual feedback could increase forward propulsion, increase walking speed, and in the same time increase metabolic costs during walking. However, the effect of real-time peak propulsive force feedback on people with amputation is unknown. In some additional studies have used the other feedback types, such as spatial temporal feedback or kinematics feedback as a real-time feedback for people with lower limb amputation, which reduce the gait symmetry and metabolic cost in this group of participants. Therefore, this study aims to assess the effect of real-time visual feedback of peak propulsive force during walking in people with unilateral transtibial amputation. And we're interested in answering 2 questions. One is that if they're able to achieve a higher peak propulsive force, and the second is that can the effect of visual feedback be retained when the feedback is withdrawn? So we so far recruited 4 participants, and they all walk with their own passive prosthesis during walking. We asked them to walk for 5 minutes at 1.25 meters per second for a baseline trial, and then a series of visual feedback trials, and then a series of retention trials afterwards. And we have participants we gave them 5 minutes in between each trial to rest, and we compared visual feedback trials and retention trials to their baseline trial. During visual feedback trials, we placed the monitor in front of the participants, and on the screen, we presented peak propulsive force measured from both legs, and the training target that was equal to or 20%, 40% higher than their baseline peak propulsive force from their affected leg. We instruct the participant to match the target for peak propulsive force from their affected leg. If their peak propulsive force from the affected leg met the training target, the horizontal bar would turn green, otherwise it was red. Exact verbal instructions were given to every participant before the beginning of the feedback training. We removed the visual feedback during the retention trials. We collected ground reaction force during all trials. So far, we analyzed the data from the last minute of walking. So now let's look at the results. So first, we're gonna take a look at the peak propulsive force. The y-axis here shows the percentage difference compared to their baseline trials, with the 2 dotted lines marking the 20% and 40% training target. And we can see that participants did increase their peak propulsive force when walking with visual feedback, but they did not match the training target precisely, and they showed variance in their peak propulsive force. Moreover, the effects of visual feedback were not retained during the retention trials. Now let's look into some individual response to visual feedback. Each participant was plotted here using a different color. We noticed that there is an individual variance to visual feedback. For example, subjects 01 did not respond to visual feedback compared to the other 3 participants. Next, we calculate the symmetry index of peak propulsive force using an equation shown here with 0% indicating perfect symmetry. And here is the average symmetry index on the y-axis for the baseline trial, with the symmetry index a little bit above 40%. When walking with visual feedback, we can see that the symmetry index reduced, indicating that the participants were walking with less asymmetrical peak propulsive force. However, this effect is not retained during the retention trials. Here shows the average symmetry index on the y-axis of the 4 individual participants from the baseline trial. When giving visual feedback, subjects who were able to increase their peak propulsive force also had a reduced symmetry index, which are subject 02, 3, and 4. However, this effect was not retained when feedback is withdrawn. Our current results supported our first hypothesis because participants increased their peak propulsive force during visual feedback trials and reduced the symmetry index. However, our results also suggest that the effect of visual feedback is not retained after 5 minutes of walking with no visual feedback. This may be due to a short feedback time of only 5 minutes. Moreover, we have only analyzed data from the last minute, and we plan to further look into the data from the first and third minutes of walking, which may provide us with more information. So this is the study is funded by Department of Veterans Affairs, and we also have a poster in F51, which talks about visual feedback and metabolic cost given by my colleague Helen, and this is my email. Thank you very much.
Thank you for an excellent talk. We're going to move on to Courtney Budowitz.
All right, can you guys hear me?
Yes, thank you.
Awesome. So today we're going to be talking about low back pain and how it influences coordination during standing balance in persons with lower limb loss. Quick disclaimer, the views expressed here are those of the authors and do not necessarily reflect any official policies or views of the US government or the Department of Defense. So compared to the general population, persons with limb loss have higher prevalence rates of low back pain. This has been reported as high as almost 90% versus 30% in the general population. And individuals with limb loss also often demonstrate impaired balance and trunk postural control. In terms of balance, standing balance is sustained through multi-joint coordination of postural responses. Low back pain alters these responses by shifting from an ankle dominant strategy to more hip dominant strategies, which are important because given these strategies are associated with poor balance control. However, the extent to which trunk lower extremity coordination patterns impact center of mass variability during standing balance in persons with limb loss, particularly those with low back pain, is relatively unknown or misunderstood. So the aim of the study was to determine the influence of these coordination strategies on center of mass variability during standing balance among persons with lower limb loss with and without low back pain. We hypothesized that trunk-hip coordination would be the predominant pairing predicting center of mass variability among those with low back pain. So we collected data from 40 persons with unilateral lower limb loss, both transtibial and transfemoral. Participants were asked to stand quietly with their eyes open and eyes closed on a firm surface for 30 seconds in each condition while wearing 8 IMUs. A state space model with a Kalman filter was used to estimate 3D orientations of the sternum, sacrum, and each lower limb sensor to calculate hip, knee, and ankle joint flexion extension angles. Participants with low back pain were identified by a self-report using a body pain map and reported the intensity of their pain on a 0 to 10 scale. Using variability in the lumbar angular velocity, fuzzy entropy was used to characterize center of mass variability. Normalized cross-correlation function were used to identify coordination patterns between the trunk and hip, trunk knee, and trunk and ankle. We use multiple linear regression to predict center of mass variability from peak positive and negative cross correlations for each pattern, with body mass and amputation level as covariates. So for our results, with the eyes open, trunk lower limb joint coordination on either the intact or the prosthetic limb did not predict center of mass variability, regardless of group. However, in the eyes closed condition, trunk lower limb joint coordination on the intact limb predicted center of mass variability in the low back pain group. The primary contributor here was positive trunk hip coordination, but we did not see a similar result in the no low back pain group. On the prosthetic side, we saw the same thing where trunk lower limb joint coordination patterns predicted center of mass variability, but now the inverse was true where trunk hip coordination was the primary contributor on the prosthetic side. We did not see any relationship in the no low back pain group. Notably in the low back pain group, the trunk lower limb joint coordination patterns predicted nearly half the variance in center of mass variability in the eyes closed conditions. So what does all this kind of mean, I guess? So we know from this and other studies that vision is likely the dominant source of balance stabilization in this population, which may increase fall risk when visual feedback is compromised. Persons with limb loss and lower back pain appear to demonstrate an opposing coordination strategy between the lower limbs and center of mass, such that there is a flexion-flexion pattern on the intact side and extension-flexion strategy on the prosthetic side, which appears to be related to the presence of low back pain. The utilization of altered proximal control strategies combined with an inability to regulate kinematic variability of the trunk in this population, particularly those with low back pain, perhaps creates a scenario where the demand to control the center of mass exceeds the ability of the neuromuscular system to efficiently do so. This is particularly relevant for service members who have returned to active duty, as they can carry 40 to 60 pounds of tactical gear above the waist in the field, which could potentially further challenge center of mass control. I'd like to thank our colleagues and our funding sources. And with that, I will be happy to take any questions.
Well, thank you very much for the talk. Questions are flying in chat. We're going to keep moving on. We may have a little bit of extra time at the end, but our last speaker is going to be Shay Pinney. We can't see your slide yet. Great, and we do have John here too, so we'll be able to have our full session. Are you able to share your screen again, Che? Oh, I have a direct message. She's not able to share her screen or unmute herself. We might have to look to our technical support here.
Maybe
Okay,
John can
got it
try.
now.
Okay.
There you go. All
Thank
right,
you.
great.
All right, I think we're all good. Hi, everyone. I'm Shay. I'm from Northwestern University, and I'm going to present today on how unilateral transfemoral prosthesis users rely heavily on their sound limb during walking. So this study was performed at the Prosthetic Orthotics Center at Northwestern University and in collaboration with the National Institute of Advanced Industrial Science and Technology in Tokyo, Japan. Walking requires that work be exchanged from step to step to keep the body center of mass moving forward. As the leading foot contacts the ground, physiological mechanisms absorb collision work, and then when the foot pushes off the ground, the body must generate that lost work in the form of push-off work. The physiological mechanisms which perform this energy exchange are altered or impaired in above-knee prosthesis users. The presence of a lower limb amputation disrupts the ability for restoration of energy loss through control of the ankle joint. Additionally, hip control is required by the prosthetic limb side to ensure proper knee function and prevent buckling, as well as prepare for swing phase. The contralateral sound hip also faces additional demands to keep the body moving forward. These compensations require specific timing and are dependent upon walking speed. This study therefore aims to assess the effects of walking speed on step-to-step energy exchange in unilateral transfemoral prosthesis users, with hopes to gain insight into the mechanisms employed by these prosthesis users to maintain forward motion. The hypotheses for this study are twofold. The first being that collision work will increase with walking speed for both limbs, and the second being that the prosthetic limb will display reduced push-off work across speeds. For this study, 25 unilateral transfemoral prosthesis users participated and walked on the split belt instrumented treadmill, which collected ground reaction force data. The participants walked at 8 different speeds for 30 seconds each. To get from ground reaction force data to body center of mass work, we used the double inverted pendulum model of walking and performed calculations which have previously been outlined in a paper by Donlan et al., and this can be seen in the bottom right figure. We broke walking up into 3 phases. This can be seen with the pendulum diagram and with the corresponding same color shaded area on the power plot. The 3 phases were collision phase, which is the first double support phase. This is shown in blue. And then the mid stance phase, which is in red. This is the single limb support phase. And finally, the push off phase is in orange. And this is where the limb pushes off as the opposite limb goes into collision phase. The work for each leg was calculated separately to help identify where compensations are being made in transfemoral prosthesis users. So these graphics outline our results for the prosthesis on the left and then the sound limb on the right. So each of the 8 walking speeds is on the x-axis and the work output, which is normalized to body mass, is on the y-axis. Each point here represents the mean work output that's averaged over all 25 subjects at that speed. The blue lines on both plots represent the collision phase. So we see here that for both limbs, as speed increases, the collision work becomes greater or more negative. For the mid-stance work, which is shown in red, it's nearly flat across all speeds for the prosthesis. But you can see that on the sound limb, there's a jump, especially after 1 meter per second. And this may suggest that positive work is being maximized through mid and late stance on the sound limb to compensate for that energy loss due to the absence of prosthetic limb push-off. Looking at the black line, this is push-off work, and it's interesting to see that as speed increases, the sound limb values at all speeds are greater than any push-off work for the prosthesis, which is unsurprising with the lack of ankle to actively push off on that prosthetic side. Our first hypothesis was supported as we see that both limbs increase in collision work as walking speed increases. Our second hypothesis was also supported as the prosthetic limb produced less push-off work as compared to the sound limb at all speeds. It was previously theorized in transtibial prosthesis users that the reduced push-off work by the prosthetic limb would lead to greater collision work on the sound limb, but this was not seen in our transfemoral prosthesis user data.
And in fact, the difference between the sound limb and prosthesis limb collision work was not significant across speeds. For the sound limb, both push-off work and mid-stance work significantly increased with speed, but for the prosthetic limb, mid-stance and push-off work was nearly constant. This supports previous findings that the sound limb is facing considerable hip demands to continue forward progression. So the bottom line here is that we found the prosthetic limb is essentially an energy sink. It's simply just supporting the body as it transitions over the prosthesis, but not providing any power. Along with this, we found that the sound limb is responsible for almost all energy changes that occur with speed. This emphasizes that the sound limb may be at risk for overuse effects, and this could affect its musculoskeletal health. Future work should look at the joint level contributions to help further assess where interventions to enhance prosthetic limb push-off can occur and diminish the potential of overuse to the sound limb. Some references, and that's all. Thank you guys for listening.
Thank you for the excellent talk. We're going to move on to our last speaker in the hopes of having 5 to 6 minutes for questions. And our last speaker is John Chomak.
All right. Hi, everyone. Can everyone hear me?
Yes.
All right. Okay. All right, so I'm going to try and get right into it. Thank you for the introduction. My name is John Chomak, and my presentation today is the effects of powered ankle foot prostheses on intact knee adduction moment. This investigation is just one component of a larger study titled The Criteria for Advanced Prosthetic Foot Prescription. It's part of a larger study born out of the clinic where there are hundreds of different types of prosthetic feet out in the market, along with minimal instruction on how to precisely prescribe a patient a foot. And seeing most clinicians base their prescriptions on manufacturer-driven research or anecdotal evidence based on what they know to have been useful for similar patients. We're seeking to standardize this prosthetic prescription process by selecting prosthetic feet that allow for the greatest amount of functional independence and comfort. Our approach uses functional outcomes, subjective questionnaires, and biomechanical assessments to compare 3 types of prosthetic feet. We have an energy storing return foot, an ESR foot with articulation, and an articulating foot with power. A particular component of the study is the use of the power articulating foot, the Empower foot. It is currently the only commercially available ankle foot prosthetic device able to provide the user with biomimetic power generation at push-off. Often, as a result of amputation, secondary musculoskeletal comorbidities such as knee osteoarthritis occur in the intact limb due to increased loading from various compensations, coupled with asymmetrical gait. It is known also that the first peak of the knee adduction moment is a good measure of the medial-tibiofemoral joint loading, but also at high values may indicate osteoarthritis. Results from previous studies like Robotic et al. Looking at the first peak of the intact knee adduction moment using this device, comparing it to an ESR foot, show the first peak reduction of 21 and 12% at 1.5 and 1.75 meters per second, respectively. We then hypothesized that the use of the power device would significantly reduce the first peak of the intact knee adduction moment with respect to both ESR and articulating devices and would be normalized to control groups. As a reference here, we have one participant's data. In figures A through D, we have the user wearing a conventional ESR foot, and in figures E through H, a powered device. Some differences between the ESR and power devices between the intact and prosthetic sides are the gait cycles are more symmetrical throughout within the power group. The reduction and the increase of the first peak of the knee adduction moment for each limb respectively. The ability for plantar flexion at terminal stance into toe off for the prosthetic limb, and near equal power generation in the ankle. Our biomechanical data sets were collected from visits on days 28, 35, and 42 from our participant timeline. We ran a one-way repeated measures ANOVA looking at the first peak of the intact knee using the prosthetic device versus the control, and then between the Empower and each device by speed. Our goal was to have 30 out of 100 participants run through our biomechanical procedures. Currently, we have 18 analyzed along with 8 control participants. Between the control and experimental groups, there is a significant age gap of 20 years. We are aiming to collect a similarly aged control group to reduce the risk of age as a compounding factor. Our results from our ANOVA show there are no significant differences found between intact limb devices and the control, but also between the Empower and the ESR foot for each speed. However, while there are no significant shown for the intact side, on the prosthetic side, we did see the Empower with the lowest first peak at each speed. So taking the average of the knee adduction moment at each speed, we conducted a descriptive analysis between each of the 4 groups, seen in figures A for 1.0, B for 1.3, and C for 1.5 meters per second. For all the figures, we see a minimal separation between the first peak of each group. The largest difference occurs in figure B with the ESR and the Empower with a difference of 7.14%. This is the only point we see a lesser intact first peak with the Empower rather than the ESR. And furthermore, in figure C at the highest speed for all groups, we see a trend towards near equivalence for the first peak of magnitude. Other research has shown significant differences between the ESR and Empower devices occurring at this speed. And we believe if we continually increase the speed from this point, we might start to see separation. Conversely, participants might have difficulty ambulating at this level, and we would start to see unnatural gait. Since there are no significant differences, we briefly explore the difference between intact and prosthetic sides. In figure D, we have each group average from all speeds, and from which we could see the degree of symmetry between intact and prosthetic sides are only present in shape but not magnitude. And unlike the representative data, the power foot does not produce a similar biomimetic symmetry or reduce the intact first peak. This may be due to various compensatory actions developed by our participants, and more specifically, the effects of the sagittal plane power provided during push-off by the Empower on the intact limb. And this may be limited by the uniaxial design of the device, which cannot truly replicate the biarticulate nature of the gastric soleus complex. So again, our hypothesis was the power device would significantly reduce the first peak of the intact knee adduction moment with respect to both ESR and articulating devices, and would be normalized to the control group. In our current data set, we found no significant differences between an intact limb using the devices and the control, or with the Empower compared to the other devices at any speed. It may be possible to view significant differences with more trials at greater speeds. Since our results stray from our hypothesis and previous research, our future work will investigate assessing the age gap between the subject pools, the relationship between timing and the magnitude of peak knee frontal angle, force generation and its first peak, and the loading rate, and step-to-step transition work. Assessing these parameters in conjunction with our current data set may provide us a more precise picture of participants' compensatory actions and how it affects intact knee adduction moment. I'd like to thank everyone for allowing me to join, our collaborators and CDMRP for sponsoring this study.
Thank you very much. I'm going to hand over the moderating duties for our questions to Helen Huang in the hopes that we can get 1 or 2 questions in for this block. The spatial chat has been put into the chat, and we hope to see you all there.
All right, thanks, Daniel. So we have, since Jenna went first, she has the majority of the questions. I'm going to combine some of the questions. So there's a question about, can you identify any specific differences between subjects who did and didn't respond to the feedback? And some other folks, someone was asking about maybe there's a difference. Well, I'm saying maybe there's a difference because of initial verbal cues. They were curious if there are any differences in verbal cues. And then someone else was curious about any changes in whole body dynamics.
Yeah, I'm actually very glad somebody asked that question. I'm just going to quickly show some of the results that I didn't have time to present. So first of all, the reasons for why somebody responds well and somebody did not. We find that subject 01 has a relatively higher peak propulsive force in her unaffected leg. So her walk with a pretty symmetrical peak propulsive force in her baseline trial as already. So I suspected that might be the reason that she did not really respond to our visual feedback. And for the joint level kinematics, we did calculated the peak ankle power, which is presented here, that we find on average that with visual feedback, participants increased their peak ankle power, even though this is a passive prosthesis that we used. So our next step, we also have this group of participants walked with powered prosthesis. And so we're going to analyze that group of data later. And verbal cues on how they should do it. No, we did not ask them how to do it. We just give them instructions, see how does feedback work, but you can do whatever you think that should work. I hope that answers the question.
Right, great, thank you. We've got a couple, let's see, we've got a question for Courtney. How might you extend your work among low back pain treatment modalities? Could you use these balance tests to monitor long-term health outcomes during low back rehabilitation?
Sure, great question. I think the use of IMUs allows us to really kind of expand our analyses in the clinic, particularly pre and post treatment. These really, the technology's come a long way. It's still not exactly where a lot of us would like it to be, but I think there's some clinician friendly options out there that allow us to quantify biomechanical variables pre and post treatment. And balance tests are just one piece of the puzzle. I think a comprehensive assessment of balance and isolated trunk postural control is probably going to be your best bet there.
All right, great, thank you. And I guess we'll sneak in one last question. The last question in the chat is for John. How did you tune the biome?
Yes, so we actually use the successor to the biome, the Empower, and that comes with its own software on a tablet where you can adjust for time delays and power for different speeds, slow, normal walking speed, and fast. We did an initial programming of the device during a pre-acclimation period, and then participants were allowed to go home with the device for a whole week to acclimate. And upon return or midweek, if they needed adjustments, we were able to adjust that again prior to testing.
All right, I'll turn it back over to Dustin.
Sure. Just thank you all for the speakers and attendees, especially those who asked questions, made it a great session. Thanks also to the co-moderators, Daniel and Helen. I think this is great. So join us in spatial chat if you can, and especially the speakers. Go over there and talk to people. We'll see ya. Have a good rest of the conference.